Hi, SIOS members. Leigh Stearns. I'm a professor at the University of Kansas. Thank you for letting me record this talk and show you some of the ways that I have kind of fallen into machine learning in glaciology. This year, I'm also a faculty fellow at the National Geospatial Intelligence Agency, and it's kind of reinforced my interest in learning more machine learning because they're just dealing with a ton of data. It's really exciting. Because this is recorded, feel free to reach out to me on Twitter or send me an email afterwards if you have questions or comments. So I started using machine learning just probably like everybody. And by I mean mostly my students have done the hard work. And that is just because we have so much data in glaciology, just kind of all of a sudden, so much. This is something that we had in a recently funded grant trying to use machine learning to understand patterns. And that's, often we look at glacier change through the lens of one parameter, like what's the terminus doing, what's the ice velocity doing, what's the surface mass balance doing, but machine learning kind of gives us some cool ways to integrate all that knowledge. So that's kind of one reason that we've been pursuing that over the past few years in my group. Another one is just the growth of satellite imagery. And there are estimates that by 2030, small sats will image everywhere on Earth under 10 minutes intervals. So, we're just seeing a lot of data and we need to be able to use it intelligently. And so not saying that I figured that out, but there are some cool things that we can use machine learning for. And I don't want to get too technical here because I think you guys will be doing that a little bit later in this course, but there are many different types of machine learning. We kind of lump them all into this one, artificial intelligence, machine learning, huge umbrella. I'm mostly dealing in this realm of supervised learning, and that's often kind of split into classification and regression. Classification is like usually more categorical. In the real world, they use that for like customer type and ages and that kind of stuff, whereas regressions are more numeric, like sales predictions and weather forecasting. You can see that. And because we've mostly what I'll talk about is kind of image classification, it falls in this category. And just so you are kind of putting things into context for lingo, there are kind of a few key ways that those classifications are done, a few different methodologies. Support vector machines, which we're starting to use actually in our lab as kind of an efficient way of doing some different segmentation. It's a lot faster and less cumbersome than neural networks. Neural networks are just kind of another, usually more intensive kind of learning way of doing things. Each neuron is kind of learning as it goes. And random forest, which is a decision tree format. And so I'm not going to really go into the details of it. I just want to show you kind of how we're applying it, which I think is the fun part. But just want to let you know that my work, we're only dealing with this like small arm of this huge machine here. And there are many different ways that other techniques could be used for glaciology. It's just not what I've been doing so far. So I want to first start with random forest. It is kind of the more simple one in terms of its efficiency and its kind of computer costs, which for academics is really important. But with my role at NGA, they're like, oh, we can, we have all this server and computing power that we need to do the really kind of laborious and cumbersome tasks on huge scales. As academics, we don't do that because we don't have the resources. And so we've used a lot of random forest to detect icebergs all around Greenland. And one advantage of that is that it is a machine learning algorithm within Google Earth Engine. The other neural networks, Earth Engine doesn't have kind of the cloud computing to do that on the fly like it can for random forest. And so this is a project that my student Sid has been wrapping up, looking at Sentinel-1 SAR imagery all around Greenland every 2 weeks and identifying, using random forest, all the icebergs out to 150 kilometers from the coast. So here's just a kind of a raw image of the Sentinel one seen, and then his detection of icebergs. And so we would not be able to do this with any other way, and kind of past ways of finding icebergs around Greenland, have not been so systematic or consistent. So we can do this every 2 weeks for 5 years. And that lets us address some pretty interesting science questions. With any machine learning algorithm, of course, we have to like prove that it's been successful and quantify where it's failing. We're looking at every single background environment: sea ice, open water, waves, melange. And when we look at pixel by pixel comparison from our manually traced icebergs to the ones that our random forest algorithm is finding, we get 91% detect kind of true negative, so it's not an iceberg and it's classified as not an iceberg, and then about 74% of classification for an iceberg. When we don't consider the melange, which as glaciologists we're interested in, but the rest of the community probably isn't, so if we can just cut that part out, then our true positives do increase to roughly 80%, which is really pretty good. Again, this involved a lot of kind of tricks with the training data. So for every machine learning algorithm, you have to really be careful about what you're training for. So if we only trained by tracing icebergs in one environment like the melange, then it would not do a good job finding those icebergs in open water or waves. And so we have to make sure that we're covering all the environments we would find it in order to teach the model how to operate there. But this kind of operation allows us to get results like this. And I know this is super, super busy, but we've divided the ice sheet up into these 30 some odd grids. This is actually just showing the percent of fjord area in each grid that's covered by icebergs every 2 weeks. And it goes from 1 to 32. So it's a little hard to read, but just to give you a sense of the wealth of data that we can get, it took a while to build the codes and get everything operational, but the system works pretty efficiently now that it's running. It can crank through a whole mosaic of the ice sheet, in under a day. And actually, I think it's just a few hours now. So that is really, we couldn't do that, 4 or 5 years ago. That's pretty exciting for us. So that's random forest, which is really pretty fast. And, incorporating Earth Engine, which is a huge advantage for us in our image classification. Another code that we've been working on is, again, kind of same application of finding icebergs in Greenland fjords using a neural network, which does a probably better job than random forest. And you can see a little bit of the results here. So in many cases before, without using machine learning, we were just doing a thresholding of the brightness. So here's a Sentinel-2 optical image at 10-meter resolution. You can see the icebergs in the dark water. And if we just say anything brighter than a certain level is an iceberg, it does an okay job, but it thinks, it mushes these into one big iceberg down here, thinks that this cloud, because it's bright, is an iceberg. And so there are a lot of things that it's not capable of doing. Part of that is the image resolution, but a large part of that is that classification scheme. And so here's a planet image, which is a higher resolution commercial small sat. First, right away, because the imagery is a lot higher resolution, you can see the icebergs better. And this neural network called UNet allows us to weight the kind of important characteristics of the icebergs better. So we're saying the edges are really important. So that allows it to kind of separate icebergs that are close together, which is really, in terms of operational and logistics, what people navigating the Arctic want to know where small icebergs are. They can see the big ones pretty clearly, but they want to know where the small ones are. And so using techniques like this will be really, really helpful. For our kind of science purposes, it allows us to find smaller icebergs, which is really exciting. If we just use kind of this technique, we get an iceberg distribution. So here's the area, surface area. This is relative abundance. So it's, you can just kind of think of it as being upside down there. So there are a lot of small icebergs. This would be the distribution we get in just thresholding it. In this example, where we use planet imagery and UNet, we're finding a lot more smaller bergs and also kind of shifting that line a little bit of the distributions. You might not think that's a big deal, but if we're all of a sudden finding smaller icebergs, they're not going to last as long in the fjord. So here's the frequency of these different size icebergs. And if we apply a melt algorithm to them, we can figure out kind of roughly how long they'll last. So most of the icebergs with our new technique don't last more than 10 days, whereas the sentinel imagery and that thresholding technique lump them together, and then they don't melt as quickly, and they kind of advect out. And that has also kind of big implications for how much just fresh water they're adding to the system. So these kind of differences become pretty important. And then the last kind of classification scheme that I wanted to show is using a different convolutional neural network kind of pair. One is object detection using YOLO v4, and this is all open access, publicly available, really extremely fast. These algorithms don't find the exact shape like the other ones do, but find a bounding box, which is for many applications good enough. And it outputs this detection probability. So all these are numbers, like this very fuzzy one and this small one have a lower probability because the algorithm isn't so sure. But these ones have 90%, 95% probability. They're a lot clearer. With that object detection, we can also track them, which is using this algorithm called Deep Swart, which was really developed for like surveillance. We don't develop things very rarely in earth science for the things developed for us. We just kind of try to steal the open access stuff that we can that's useful. And it has the advantage of tracking objects for long periods. It's not impacted by occlusion, which means you can lose an object for a number of scenes and then find it again based on its shape and its parameters. Really, this is designed for these very high spatial resolution and high temporal resolution video files. So they're not designed for like a 10-meter resolution SAR image taken every 3 days, which is what we have publicly available. But in the future, we'll probably have more commercial satellites that are getting imagery more readily, and this will become more viable. But it allows us to do things like this, which I think is pretty cool. Each of these are an iceberg ID. Here's Helheim Glacier and its melange. So all the icebergs are moving from left to right here. And so this is the day of year. And you can, follow a few icebergs, like 39 was there. We lost it a little bit. It'll appear in a few images, and we're kind of following its path out to the open water. So this would be impossible to do manually or really with any other algorithm, but we can use these ones that have been developed for other purposes for the things that we're interested in. So that's what I've been doing, and what I've been explaining are the applications for kind of image segmentation. We've also applied these to look at like automatically tracking the terminus of the glacier, how it changes, week to week, to inform us about calving processes and frontal ablation. We've been looking at trying to classify different crevasse patterns and what that's telling us about, how they are important or not important for the calving style of different glaciers. So there are a lot of applications that are really exciting that we can apply these to. The last one I wanted to talk about is really looking at the synthesis of data that we have. So I showed at that table, the second slide, of just all the publicly available data we have now, which is incredible and really exciting. But trying to make sense of it is hard. And so this is using kind of a time series forecasting algorithm called long short-term memory, LSTM, to analyze glacier behavior and potential drivers. And so the training is done on the period before this dashed line here. So this is for Rink and this is for Helheim. Let's just focus on Rink for now. So we have the measured runoff, reanalysis, measured runoff, monthly or something for Rink, and we're giving that information to the algorithm. We also know the terminus position, feeding that to the algorithm, and we know the ice velocity. And what we want to do is predict the velocity into the future. And so we train everything up until 2013. All these algorithms need a lot of training data, which is hard, especially prior to 2009 or so, we didn't have good winter velocities and winter observations. So filling those gaps is tricky. And then after 2013, we feed it the observations for these past few years, 2013 through 2016. And we ask the model essentially, what has the velocity done if you just give it these parameters? And you can see that the velocity is predicted pretty well. And then for Helheim Glacier, however, all of a sudden, same thing, we train it up to 2017, and then we predict its future past that. And it doesn't do a good job kind of in this last year, because all of a sudden it's retreated beyond the scope of what it's been trained for. So, this is an interesting example, and I think can be carried forward. We're only using a few parameters: runoff, terminus, and velocity, and we're not using anything about geometry and ocean and all these other parameters that are probably important, and that in this new grant we will dig into. But if it's a predictable glacier, we can predict it quite well. If it's doing something out of its training regime, we can't really predict what it's going to do. So that's just something that in all of these cases, it's good to know that you can't predict things that you haven't trained it on before. And that makes it, those are just some of the limitations of these models, but really cool that you can say, now we can say, that velocity is more dependent on runoff or terminus position than anything else. So we can kind of figure out where those correlations are, which is pretty cool. So I'll just end. I know I'm at 15 minutes. There's a lot of kind of what you get in is what you get out, and it's sometimes hard to interpret what you get out. And so it does take kind of a lot of thought to build the machine the right way. So it's answering a specific question that that you're getting at. You can't just kind of throw data at it and expect an amazing result. So ask the right question and build your model that way. Thanks so much. Reach out if you have questions. Bye.